Greetings, let's get right to it. Here I'm supposed to determine the relative growth rate between f and g. This is just a straightforward application of the definition. So I will test the limit as x approaches infinity of f over g, and if it comes out to be 0, I know g has a larger order of growth, and if it comes out to infinity, I know f has a larger order of growth. So let's see what it comes out to. So the f function is log base 7 of x to the 1/15th. The g function is log base 2 of x to the 1/3. I'm going to go ahead and simplify this right away by bringing the exponent to the outside. If you didn't do that, it's okay. This same process will work out exactly as before. It will just take a little bit longer and be slightly messier. All right. I'm not drawing equal signs here because I would need to continue writing my limit statement if I wanted to claim that the two things were actually equal. All right. So as x approaches infinity, first notice that both numerator and denominator approach infinity. So that's an indeterminate form. So that means that we can apply L'Hopital's rule. So I'm going to rewrite it down here. X approaches infinity of f prime over g prime. So the derivative of the numerator here, I've got 1/15th times 1 over natural log 7 times 1 over x. So that's the derivative of the numerator. Derivative of the denominator, I'll bring down the 1/3. This is still log base 2x, and this is now negative 2/3, times the derivative of the inside, which gives me 1 over natural log 2 times x. All right, let's simplify what we can simplify here. So this is going to come up into the numerator. Because this is a negative exponent, it's really 1 over all this business. So that's also going to come to the numerator. So here in the numerator so far, I have natural log 2x, which came from here. This 1/3 can also come up. So here's a 3. This business can also come up. So I got log base 2x to the 2/3. And then this stuff is all in the denominator. So here I've got 15. Here I've got natural log 2. Here I've got x. Let's observe what's canceling. Oh, sorry, the limit is still there. So we're still looking limit x approaches infinity. So the x's cancel. 3 cancels here, leaving 5. Natural logs 2's cancel. So the only thing left in the denominator is 5, which is a constant function. What's left in the numerator is this function, but it's definitely an increasing function. As x is going up, this is definitely increasing. So that means this equals infinity. Therefore, in the original function, f must have a larger order of growth than g. So I'll write that this way, f larger order of growth than g. All right, so based on that, which of the following statements are true? Remember, big O of g equals f means that f is a larger or equal to order of growth than g. G little o of f means that g must be a smaller order of growth than f. So, since f is a larger order of growth than g, this one is not true, but this one is true. Because, again, big O of g equals f means that f is a larger order of growth than g, which is what we have. And so then the little o is going to be the reverse of that, so it should be this one. So those are the two that are true. All right, let's continue on. This problem is also a very straightforward partial fraction decomposition. So here I can write I want to be able to rewrite this as 3 separate terms. So I'll multiply through by the denominator on both sides. So that gives me 4 equals a times x minus 2 times 2x plus 1, b times x plus 3 times 2x plus 1, c times x plus 3 times x minus 2. All right. I got to find out what are a, b, and c. So let's plug in x values that will eliminate some of these terms. If I plug in x equals 2, that eliminates a and it eliminates c, because each of these linear factors are going to be 0. So that yields an equation 4 equals b times, this is going to be 5, and this is going to also be 5. So that means if I divide by 25, I get b equals 4/25. Let's plug in x equals -3 now. That eliminates this term and this term. So now I've got a times -5, and this is -6 plus 1, which is another -5. So again, dividing by 25, I get that a equals 4/25. Last of all, let's plug in -1/2. So that eliminates this term, and I'm left with my c term. So I get 4 is the same as c times, let's see, this is 2.5, which is the same thing as 5/2. And this is -2.5, which is the same thing as -5/2. So that's the same thing as -25/4. So let's multiply by 4 and divide by -25. And that gives me that c is -16/25. All right, so I've got my a, b, and c values. So I can rewrite my original integral split up into pieces. So I've got integral a over x plus 3 dx plus integral b over x minus 2 dx plus integral c over 2x plus 1 dx. So the original is equal to that thing. I'm going to, since a, b, and c are all constants, I'm going to bring them outside the integrals. So I can rewrite this as 4/25, 1x plus 3 dx. b is also 4/25, x minus 2 dx. c is -16/25, 1 over 2x plus 1 dx. All right, so now each of these integrals are easy to do separately. I know this is natural log x plus 3, so I can write 4/25 natural log absolute value x plus 3 plus 4/25 natural log absolute value x minus 2 minus 8/25 natural log 2x plus 1. Why 8 instead of 16 here? Because if I were to take the derivative of this, natural log would give me 1 over 2x plus 1, but then I would have to multiply by the derivative of the inside, which would give me an additional 2, which is where the 16 would come from. So all I did when I took the integral was I divided by 2 out here, which would cancel out for the effect of the chain rule. And then don't forget, because we're doing an integral, you've got the constant of integration on the outside, and that is your answer. All right, let's evaluate this using L'Hopital's rule. So this is, again, a pretty straightforward evaluation. Here x is approaching 3, so let's just dumbly try and plug it in. Here I've got 3 minus 3 over 8 minus 2 to the 3, which is 8. So that gives us 0 over 0, which is in indeterminate form. So I will apply L'Hopital's rule. So I'll take the derivative of the bottom and the top. So now I've got limit x approaches infinity of -1. And here the derivative of -2 to the x gives me negative natural log 2 times 2 to the x. All right, I've got a constant function on the top. I have an increasing function on the bottom. These negative signs cancel. So that means that this entire thing must be approaching 0. And now I've evaluated it. Let's do these two. These are pretty much just about do you remember what these derivatives are. So the derivative of arctan is 1 over 1 plus x squared. But here it's not arctan of x, it's arctan of 1 over x, so it'll be 1 over x squared, times the derivative of the inside, so this is x to the negative 1. The derivative of that is negative x to the negative 2. And that's good enough for me. Arc sine, so you bring the 2 down. And now I'm multiplying by the derivative of the inside. So the derivative of arc sine is 1 over square root 1 minus x squared. And that's it for those two problems. All right, let's do this differential equation problem. So it says P of t is the population of wolves at time t years when t is greater than or equal to 0. So the population is increasing at a rate directly proportional to something. So what we're really saying is that P prime, the rate of population growth, equals something. So part A is saying express that information as a differential equation. So I know the rate of population growth is dp dt. It's saying that that is proportional to this business, so I'll write that business. Because it's proportional, that means that it is a constant times that value. So that's part A. I've just written the differential equation. Part B is saying essentially solve the differential equation using this initial condition. So I'll separate variables to solve. I'll divide both sides by this term including p. So that gives me 1 over 800 minus p dp. And I'll multiply both sides by dt, giving me k dt. Now I can throw up some integrals. On the right-hand side, I have kt plus c. On the left-hand side, this is a natural log. So I have natural log 800 minus p. But be careful, because the coefficient on p is negative. If I were to take the derivative of this, you would have to use the chain rule, and so multiply by the derivative of negative p. So I have to have a negative on the outside here that would cancel out for that. All right, because I want to isolate p here, I'm going to keep simplifying this until I can get p by itself. So I'll multiply both sides by negative 1. And actually, I'm going to call this k sub 0 and c sub 0, and then I'm going to define k to be the opposite of k sub 0 and c to be the opposite of c sub 0. So essentially, I'm just absorbing the negative signs into my constants. I'm going to exponentiate both sides, so I'll have 800 minus p equals e to the kt plus c. But then, again, I'm going to split this into two pieces, so it's actually e to the kt times e to the c. And I'll define a constant a sitting here out front, where a is the same as the old e to the c. So far, so good. I'll add p to both sides. I'll subtract this blob over to the other side, and that gives me that p is 800 minus a e to the kt. I'm almost there. But part B says just in terms of t and k, and here I still have this a value in here that I need to evaluate for. So let's plug in what we know. At time t equals 0, the population is 500. So 500 equals 800 minus a times e to the 0, which is 1. So that means a must be 800 minus 500, or 300. So that will finally let me rewrite this thing as p equals 800 minus 300 e to the kt. So that's the end of part B. Part C gives us another data point that we can use to evaluate for k. So I'm going to start part C right here. So my population is 700 when time equals 2. So I'll write 700 equals 800 minus 300 times e to the k times 2, because t is 2. I'll subtract 800 from both sides, so that gives me a negative 100 over here. I'll divide by 300 on both sides, sorry, negative 300 on both sides, So that's going to give me a 1/3 equals e to the 2k. I'll take the natural log of both sides, and I'll divide by 2 on both sides, giving me k is this value, which I shall now approximate on my calculator as negative 0.
Good afternoon, staff.
Which I shall now approximate as negative 0.549. All right, so the last part, part D, says I should evaluate the limit as t approaches infinity of that equation. So we'll write that. Let's see, my full equation was the result of part B over here, so it's 800 minus 300 times e to the negative 0.549t. Because this exponent is negative, that's really the same thing as saying 1 divided by that increasing function. So as t approaches infinity, this entire term should be approaching 0, which leaves the eventual limit as a population of 800. That's the end of problem 6. This next problem I thought was one of the harder ones, but it only actually looks hard. I'm going to show you 3 different ways to do it. The first is actually just the straightforward thing that might occur to you first, but you have to kind of keep the faith. So here we are, we're evaluating the limit of this statement. Kind of intuitively, I want to think about what I think it's going to approach. I've got a linear function on the top, and I've got a square root of an exponential function on the bottom, so I believe the denominator is growing much, much faster. So I believe this entire thing should approach 0. The most straightforward thing to do is to actually try to evaluate it. So this is going to approach infinity over infinity, which is an indeterminate form. And that means that we can apply L'Hopital's rule. So let's do that. In the numerator, I have a 1. In the denominator, I have 1/2 times all of this business to the negative 1/2 times the derivative of the inside, which is natural log 2 times 2 to the x. All right. Notice, some people went wrong here. When they multiplied by the derivative of the inside, this somehow made its way into the numerator, which is not true. You are just continuing to multiply in the denominator here. So this piece is going to make its way into the numerator, because this is the same thing as 1 divided by this stuff, and so you can kind of invert and multiply. So all of this can get rewritten as 2 times the square root of 8 plus 2 to the x, that's all in the numerator, divided by natural log 2 times 2 to the x. All right, well, so, and this is still limit as x approaches infinity. This doesn't seem to have helped, but if we do it one more time, that should do it. So this, I'll write limit, x approaches infinity. So this is still approaching infinity over infinity, so it's still an indeterminate form. So let's do it one more time. In the numerator, I've got 2 times 1/2 times all that business to the negative 1/2 times the derivative of the inside, which is natural log 2 times 2 to the x, all divided by the derivative of the bottom. So I've got a natural log 2. I will have another natural log 2 times 2 to the x. All right, so let's see kind of what cancels and how this simplifies. So I've got natural log 2 to the x here. I've got a natural log 2 to the x there. I've got a 2 and a 1/2, so these guys cancel. Let's rewrite it one last time. So I've got limit x approaches infinity. I'm going to move all that down to the denominator. So I've got natural log 2 times the square root of 8 plus 2 to the x. Let's see, did I forget any pieces? Nope. So let's observe that this is a constant divided by an increasing function. Therefore, the limit approaches 0. So really not so hard, you just kind of had to keep going. That said, let me show you 2 completely different ways you could have done it. All right, looking at this, it seems intuitively to me as if it should be approaching 0. So let's try to show that it does by creating a sandwich. What I want to do is I want to show that this limit, it's clear that this expression is always positive, so it's always greater than or equal to 0. I want to try and find another function out here where for large values of x, it will always be greater than or equal, but it will be easier to show that this one approaches 0 in the limit as x approaches infinity. So what could I do? Let's leave the numerator the same. If I want this entire blob to be larger than this entire blob, that means that this denominator has to be smaller, because I want to be dividing by a smaller thing to keep the whole business larger. So how can I take this and make it a little bit smaller? I think I'm just going to take out that 8. So here I'll have 2 to the x to the 1/2 power. Okay, well this has greatly simplified life. Let's add the limit. This has greatly simplified life because now I have something that's much easier to evaluate. I've got limit x approaches infinity, 3 plus x over 2 to the x divided by 2. This is, again, infinity over infinity, so I can apply L'Hopital's rule. Doing so gives me in the numerator, I've got 1. In the denominator, I've got natural log 2 times 2 to the x divided by 2 times the derivative of the inside, which is 1/2. And we're done. On the top, I have a constant. On the bottom, I clearly have an increasing function, so it approaches 0. And because I know my original limit was greater than or equal to 0 and less than or equal to this limit, which is also 0, therefore, by the sandwich theorem, I have determined what this limit is. All right, let's do it a third way. One of the main things that's interfering with, well, seeming to interfere with the straightforward application of L'Hopital's rule is the square root. So it would be really nice if we could get rid of the square root. Let's rewrite this as limit x approaches infinity of the square root of this entire thing squared, like that. So now, using my limit simplification theorems, I can bring the limit to the inside of the square root here. So this is the same thing as limit x approaches infinity of 3 plus x squared, 3 plus x, quantity squared, divided by 8 plus 2 to the x. And now it becomes very easy to evaluate using L'Hopital twice. So there you go. I've shown that the limit on the inside here is 0. And of course, the square root of 0 is 0. And that has shown us the result of the original limit statement. Understanding what's happening with this one relies on thinking clearly about what's going on with that thing in the denominator. The key is not to be afraid of it. The key is just to use your kind of natural thinking about, to sort of try and figure out what's going on with it. You had your calculators available, so one thing you could have done is just tried to evaluate very large values of x to see what's going on in that numerator, and does it seem like it's growing faster or slower or the same as a linear function. A different thing you could have done is just graphed it. Let's sort of take a look at what's going on here. So here in Desmos is a graph of the arc cosine. Wait, it was cosine, right? Yeah, good. Arc cosine of 1 over root x. It looks like it's maybe asymptotically approaching some value, but it's really not obvious what that is. So let's think about it this way. As x is approaching infinity, the value on the inside of the arc cosine is 1 over something that's approaching infinity. So that means this whole thing must be approaching 0. So let's look and see what is arc cosine of 0. Here's the regular arc cosine function, and arc cosine of 0 is, of course, pi over 2. Which you could also have figured out just by kind of thinking of what is the definition of arc cosine. How does it relate a side length ratio to an angle? So what we've decided is, as x is getting larger and larger and larger, this thing is just approaching the value pi over 2, a constant function, whereas the denominator continues to grow. So a very straightforward way to evaluate this one would have been like this with a sandwich. We can write 0 is less than or equal to the limit as x approaches infinity of all this stuff. And we know that that's going to be less than or equal to when the numerator is pi over 2. Oops, I keep forgetting my limit statements. Okay. This one equals, oops. Oh, this one we don't need L'Hopital because it's already just a constant over an increasing function, so that one's 0. Therefore, by the sandwich theorem, we have shown that this limit must also be 0. All right, here is the most popular mistake that people made. People just immediately tried to apply L'Hopital here. Some of them even went so far as to write that this equals infinity over infinity because they knew that you can't apply L'Hopital's rule unless this is an indeterminate form, and I guess maybe they were just hoping that that this was true. But if you actually tried to evaluate it on the calculator or in your head, of course, as x approaches infinity, the numerator does not approach infinity, it approaches pi over 2. So that is why the L'Hopital approaches to this problem were ineffective. All right, let's try the next one. This one, again, I thought pretty straightforward once you rewrite this in a way that lets you apply L'Hopital. So there are two ways you could have done this. I think this was the cleanest way. Rewrite this as limit x approaches 0 of x over tangent 3x. This is going to approach 0 over, let's see, so tangent is sine over cosine, and cosine of 0 equals 1, so this must, and sine of 0 equals 0, so this must also be over 0. So we've determined that this is an indeterminate form. All right, so now that it's indeterminate, we can apply L'Hopital. And in the numerator, we've got 1. And in the denominator, we have secant squared, 3x times the derivative of the inside. And now when we evaluate it, we get, well, here, let's rewrite it one more time in case you don't remember all your secant values. So secant is 1 over cosine, so this is the same thing as 1/3 times cosine squared 3x. Also limit. So as x approaches 0, cosine of 0 is 1, so that gives us just 1/3. This whole thing would have worked out as well if you'd rewritten the original one as limit x approaches 0 of x times cosine 3x over sine 3x. You could have applied L'Hopital to this as well, and it would have simplified out to give you 1/3. But I thought this was a little bit more algebraically straightforward. All right, number 10. Determine whether each converges or diverges and justify. All right, so we've got a straightforward 6th degree polynomial on the bottom. What's going on with e to the sine x? So I know sine oscillates between -1 and +1. So that means the value of the numerator must oscillate between e to the 1 and e to the -1, both of which are positive constant values. So we can do this one again with a sandwich. We can say this integral, e to the sine x over x to the 6th, and that other business is still there, must be less than or equal to e over all that same stuff. And it must be greater than or equal to e to the negative 1 divided by all that same stuff. So we've set up some inequalities. At this point, you have a couple of choices. It would be nice to be able to rewrite this so that it was a simpler expression. You could try to use the limit comparison theorem to show that this is the same order of growth as just x to the 6th, and then you would have some simpler things to evaluate. The problem with that is you would have to go through all the work off to the side of showing that this polynomial had the same order of growth as x to the 6th in order to simplify it. So I think maybe a slightly better thing to do is to actually sandwich it even more. So let's see, if I want a function, I'm going to leave e in the numerator here. If I want a function that's even larger than this one, I know that the denominator has to be smaller, so let's just make that x to the 5th. So then on this other side, this is still a constant on top, and if I want something that is a smaller function than this one, I know this denominator has to be larger, so I can write x to the 7th here. Cool. So this one, we know, converges because the exponent is greater than 1. This one we also know converges because the exponent is greater than 1. Therefore, our original one converges because we've sandwiched it between two converging functions. This is not the only way you could have done it, but I feel like this is probably the most straightforward way to think about it. Last one. The most popular thing to do wrong here was to, well, I'm not totally sure what you were thinking, but a lot of people were trying to sandwich this as if you were evaluating from 1 to infinity, which doesn't actually make sense because that's not what we're doing. Let's just take a look at the graph of this really quickly. So we're integrating between 0 and 1. And here's the function. And so you see right here at x equals 1, we have a vertical asymptote. So the question is whether the area under this curve as it's going to infinity here is actually convergent or divergent. Maybe the most straightforward way to approach this one would have been actually to find the integral. So let's break this into two. Well, so you could have tried u substitution, because here I've got a u as 1 minus x squared, which means my du would be negative 2x dx. And if you tried to plug that all in, well, let's do the indefinite integral so that we don't have to worry about the bounds for the moment. But if you tried to evaluate that, here I have root u in the denominator. I know I need to replace the dx with the du, but this is all kind of a lot less straightforward. So here I know that dx equals 1 over negative 2x du. So I can replace it there, but it's not totally obvious what's happening with all this business up here. So let's not do that. Instead, let's break it into two pieces. So I'll have integral 0 to 1 of 2x over root 1 minus x squared dx, plus the second piece, I've got 3 over root 1 minus x squared dx. All right. So this piece you may recognize as being 3 times arc cosine. Because remember, the derivative of arc cosine is 1 over root 1 minus x squared. So this integral falls right out. This integral, I guess let's make it indefinite again. This integral you actually can use u substitution on. If I introduce a negative sign here and a negative sign here, now you see that my du is negative 2 dx, which is exactly what I have. So you can rewrite this one as u to the negative 1/2, so 1 over root u, du. And then you can solve it from there. So once you've solved it, then you can just straightforwardly evaluate it from 0 and 1. Woo! Excuse me. You can just straightforwardly evaluate it from 0 to 1 to determine whether or not it converges or diverges.